Bismillah ar-Rahman ar-Rahim. This video is about the central limit theorems. Specifically, I will talk about two versions of the central limit theorem. A central limit theorem is concerned with the convergence in distribution of a given sequence of random variables, satisfying certain conditions. So the focus here will be two cases. Case one, that the sequence of random variables is an i.i.d sequence. So the random variables are independent and identically distributed, and they have a finite second moment or a finite variance. The second case, the random variables are independent. However, they are not necessarily identically distributed. And in this second case, we will have a condition that is stronger than just having a finite second moment, as we will see. Before diving into the central limit theorems, let's review the characteristic function of a random variable. And the reason for this is that convergence in distribution is facilitated by the characteristic function. In many cases, we can use the characteristic function to study convergence in distribution. The characteristic function of random variable x is this expectation e to the I ux. X is real valued. The parameter u, which is the parameter of the characteristic function, is also real valued, and I is the square root of -1. Note that the characteristic function is an expectation. This expectation may not exist, or it may not yield a finite quantity. But this is not the case for the characteristic function. If we take its magnitude, then we can employ the triangle inequality. The magnitude of the expectation is less than or equal to the expectation of the magnitude. What is this number? We have e to the I, and then we have a real number here. That's a complex number that is on the unit circle in the complex plane. The magnitude of such complex number is unity. So this magnitude is equal to 1. The expectation of 1 is 1. This means that the magnitude of the characteristic function is always less than or equal to 1. It's never infinity. And note that the characteristic function, when we evaluate it at u equals 0, we get 1. This is in contrast with, for example, the moment generating function. So the moment generating function may not exist. So suppose that x is a standard Cauchy random variable, and this is an absolutely continuous random variable, and the PDF is 1 over pi times 1 plus x squared, where x is in R. Now, the moment generating function of a Cauchy random variable, it's only finite when this parameter t, which is real valued, is equal to 0. In that case, the moment generating function is equal to 1. But if we try to obtain this expectation when t is non-zero, then we get infinity. But the standard Cauchy random variable has a characteristic function. We never face this problem with characteristic functions. In fact, the characteristic function of a standard Cauchy random variable is e to the minus and then the absolute value of u. So the tool used here, again, is the characteristic function. And the main reason is that the characteristic function exists for any type of random variable. We don't have the problems that we may encounter if, for instance, we use the moment generating function. The characteristic function is 1 when u is equal to 0, and the magnitude of the characteristic function is less than or equal to 1. What if we want to obtain the characteristic function of a random variable ax, where a is a real number? So we take a random variable, multiply it by a real number a. What is the characteristic function of this random variable? What is phi ax of u? From the definition, this is expectation e to the iu, and then our random variable is ax. But if we look at this expectation, it is expectation of e, and then we have I, and then we have x, and then we have here the real parameter u times a. This is the characteristic function of random variable x evaluated at u times a. This is phi x of au. So phi of ax of u, and this is a constant, is simply the characteristic function of x. Rather than putting u here, we put a u. A Gaussian or normal random variable with mean eta and variance sigma squared, it has this characteristic function, e to the iu eta minus 1/2 u squared sigma squared. For a standard Gaussian, eta is equal to 0, and sigma squared, the variance, is equal to 1. And so we have the characteristic function e to the minus 1/2 times u squared. Note that the characteristic function is unique, which means that if we have a random variable with this specific characteristic function, then it is a standard Gaussian. If we have a random variable with this characteristic function, then it is the Gaussian random variable with mean eta and variance sigma squared. Consider random variables y1, y2, all the way to yn. And let's try to evaluate the characteristic function of the sum of those random variables, we will see that under some conditions, the characteristic function is very manageable and very useful. Generally, if we want the characteristic function of a random variable, then that's the expectation of e to the iu and then the random variable. In our case here, it is the sum k from 1 to n of those random variables yk. We have a summation in the exponent. This is the expectation of the product. Generally, that's it. But if our random variables are independent, then the expectation of the product is a product of expectations. So here, if the y's are independent, this expectation here is the product k from 1 to n of the expectation of e to the iu yk. And this is the characteristic function of the random variable yk. So this is good. The characteristic function of a sum of random variables is the product of the characteristic functions in the case that those random variables are independent. And this will be useful in one of the versions of the central limit theorem that we will study here, the Lyapunov central limit theorem, in which we will have a sequence of random variables that are independent but are not identically distributed. If the random variables are identically distributed, then the characteristic function is an expectation. And when we evaluate the expectation, they all have the same distribution. So if they are identically distributed, all of them, they have the exact same characteristic function. So this product here can be written as the characteristic function of one of the random variables raised to their number, which is n in our case here. Note that something like the CDF, the cumulative distribution function of a sum of random variables, may be intractable. It may be very complicated to obtain. But for a characteristic function, the characteristic function of the sum is the product of the characteristic functions if the random variables are independent, or it is the characteristic function of one of them raised to their number if they are i.i.d. This is the case of independence, and this is the case of i.i.d. We need the following inequality related to the characteristic function. Note that the characteristic function is expectation e to the iuy. We can write down this exponential using the Taylor series. This is expectation of, and the Taylor series is summation k from 0 to infinity. Then we have iuy all to the power k divided by k factorial. So what do we have here? This is like this summation after applying the expectation, but we stop at n. And we are interested in upper bounding the difference between the characteristic function and this summation with n plus 1 terms. So this magnitude of the difference is upper bounded by this quantity here, which has the parameter delta. And for every delta between 0 and 1, this is a valid upper bound. And so if we want the least upper bound, then we can take the infimum of this function here of delta over delta from 0 to 1. Note that the upper bound includes the absolute moment of random variable y of order n plus delta. And there here we have the beta function, beta of delta plus 1, comma n, beta of a comma b, where these are strictly positive real numbers, is given by this integral here, integral from 0 to 1, t to the a minus 1, 1 minus t to the power b minus 1. So if we have a parameter here, it appears here minus 1, and this second parameter here, it is b minus 1. And in terms of the gamma function, beta of a comma b is gamma of a times gamma of b divided by gamma of a plus b. The gamma function, if its input is a strictly positive real number, can be written as this integral from 0 to infinity of t to the power c minus 1 e to the minus t dt. Note that if this c is a positive integer, then the gamma function, gamma of c, is exactly the factorial of c minus 1. What is this beta function if delta is equal to 1? And what is this beta function if delta is equal to 0? So if delta is equal to 0, we have beta of 1 comma n. That's gamma of 1, which is the factorial of 0. That's 1 times gamma of n divided by gamma of n plus 1. And so this is the ratio of n minus 1 factorial to n factorial, which is 1 over n. If delta is equal to 1, then this is equal to 2. We have beta of 2 comma n, and this is gamma of 2. That's 1 factorial, which is 1. And then we have gamma of n. And in the denominator, we have gamma of n plus 2, the sum of these two guys. In this case, we have the ratio. In the numerator, we have n minus 1 factorial. In the denominator, we have n plus 1 factorial. And this ratio is 1 over n times n plus 1. Because this upper bound is valid for any delta between 0 and 1, then we can choose to use this minimum as our upper bound. So we can upper bound this magnitude using the minimum of this quantity evaluated at delta equals 0 and at delta equal 1. Or we can choose one of these two terms. So again, all these are valid upper bounds that can allow us to bound this magnitude, which will appear to us as we will see. When n is equal to 1, this difference is the characteristic function of random variable y minus, if n is 1, then we have two terms. The first term is 1, and then the term corresponding to k equal to 1 is iu times the first moment of y. If we choose small n equal to 2, then we have three terms here, 1 plus iu, the first moment of y, and then we will have k equal to I squared is minus 1, then 1 over k factorial is 1/2, and then we have u squared and the second moment of random variable y. If random variable y is zero mean and its variance is rho squared, then what is the upper bound if we choose n equals 1 and we fix delta equal to 1? If the first moment is equal to 0, then in this case, this term here is 0, and the magnitude will be the magnitude of the characteristic function minus 1. This is the deviation between the characteristic function and 1. Recall that the magnitude of the characteristic function is always less than or equal to 1. Here we are studying the magnitude of the characteristic function minus 1. Now the upper bound, if we choose n equal to 1 and delta equal to 1. Okay, so this is the term corresponding to delta equals 0 and this delta equals 1. So we'll use this one here. If we put n equals 1, this will be u squared. And then we have the expectation of y squared. And since y is 0 mean, then the second moment is the variance. So this will be rho squared. And then we divide by the factorial of 2, which is 2. So the upper bound will be 1/2 u squared rho squared. What if n is equal to 2? And we want to write down this general upper bound, which is valid for any delta between 0 and 1. Now, from these three terms, since the random variable is 0 mean, this expectation is equal to 0. And then we have the magnitude is the magnitude of the characteristic function of random variable y minus 1 plus 1/2 u squared rho squared, which is the variance and the second moment of the 0 mean random variable y. This upper bound for a general delta, and if n is equal to 2, is 2 to the power 1 minus delta, and then we have the magnitude of u to the power 2 plus delta, and then we have the absolute moment of random variable y of order 2 plus delta, and then we have the beta function, beta of delta plus 1 comma 2. Is the characteristic function differentiable? It turns out that this depends on the moments of the random variable x, whether they are finite or not. So we have the following very important theorem. If the random variable x has a finite kth moment, this means that the expectation of x to the k, the expectation of the magnitude of x to the k, those are finite numbers. In this case, the characteristic function is k times differentiable. So we can differentiate the characteristic function k times. And the kth derivative of the characteristic function is expectation ix to the power k times e to the iux. If we evaluate the kth derivative of the characteristic function with respect to u at u equals 0, this exponential is equal to 1, and we get that the kth derivative evaluated at 0 is I to the power k times the expectation of x to the power k, which means that the value of the kth derivative at 0 is the kth moment times I to the power k. If k is equal to 1, the characteristic function is differentiable once at least, and the value of the first derivative at u equals 0 is I times the first moment of the random variable. If the random variable has a finite second moment or finite variance, then the characteristic function is at least twice differentiable, and its second derivative evaluated at u equals 0 is minus the second moment. Here is our first central limit theorem. That's the i.i.d. case. The random variables are i.i.d, independent and identically distributed. They are 0 mean, and they have a finite variance or a finite second moment. The claim is that the sum x1 plus x2 all the way to xn divided by the square root of n converges in distribution to a Gaussian random variable. The mean is 0 and the variance is sigma squared. This statement here is a statement about the CDF. What we are exactly saying is that the CDF of this quantity here, this random variable, which is the sum x1 all the way to xn divided by square root of n, the CDF of this will converge to the CDF of a Gaussian random variable that is 0 mean and that has a variance of sigma squared. As I said earlier, the CDF of a sum of random variables, even if i.i.d, is cumbersome. It is not something that is nice to obtain and to use in proofs and derivations. The characteristic function is much easier because the characteristic function of a sum of i.i.d random variables is just the characteristic function of one of them raised to the power their number. So it turns out that despite the fact that convergence in distribution is by definition a statement about the convergence of the CDF, but we can study convergence in distribution using the characteristic function. So there is Levi's continuity theorem, which tells us that we do have convergence in distribution if the sequence of characteristic functions converges pointwise to a function that is continuous at u equals 0. In other words, we need to, if this random variable is called, let's say, Zn, we study the characteristic function of Zn of u. We study the limit of this characteristic function as n tends to infinity. If the sequence of characteristic functions converges pointwise at every u to a function of u, and this function of u is continuous at the origin at u equals 0, then indeed we have convergence in distribution, which means that the CDF will converge to the CDF of this Gaussian random variable. Based on this, we will study the convergence of the characteristic function, or alternatively, we can study the convergence of the logarithm of the characteristic function, which is the same thing. What is the characteristic function of the sum? Note that the sum is not just the sum of the random variables. We have normalization. We divide by the square root of the number of random variables. So it is summation k from 1 to n. Then we have xk divided by the square root of n. The characteristic function of the sum is the characteristic function of one of the random variables, because we are in the i.i.d situation. We can take the characteristic function of x1 over square root n and just raise this characteristic function to the power n. This will be the characteristic function of the sum. Then we know from the first page that the characteristic function of a times x of u, a is a real number, is the characteristic function of x, and it is evaluated at au. So the characteristic function of the sum is the characteristic function of x1, and all the random variables are identically distributed, of u divided by the square root of n, and this characteristic function is raised to the power n. If we take the logarithm, this will be n times the logarithm of the characteristic function of x1. We replace square root n by 1 over alpha. Our interest is the case in which n tends to infinity. So rather, we will think of alpha as a real number, and we study the convergence of this log characteristic function as alpha tends to 0. If a square root n is replaced by 1 over alpha, then the characteristic function phi of x1, this will be phi x1 of u alpha, and then the outside factor n will be 1 over alpha squared. Our limit now is limit log phi x1 of alpha u divided by alpha squared as alpha tends to 0. Note that the characteristic function, if its input is equal to 0, then the characteristic function is 1, and log 1 is 0. If we put 0 in the denominator, we also get a 0. We are in a 0 over 0 situation. We can apply L'Hopital's rule. But note that to apply L'Hopital's rule, we will need to differentiate the characteristic function. We will differentiate with respect to alpha. Can we do this? Yes, because we are dealing with a sequence of random variables with a finite variance or second moment. According to our theorem, the characteristic function is twice differentiable. So we can actually differentiate it 2 times, not just once. So here we are justified in applying L'Hopital, because when we apply L'Hopital, we will differentiate, and the characteristic function is indeed differentiable because random variable x1 has a finite second moment. When we differentiate, we will get 1 over the characteristic function, and then we will get the derivative of the characteristic function. And by the chain rule, we are differentiating with respect to alpha, so we will get a u here outside. The denominator, when we differentiate, gives us 2 alpha. The characteristic function evaluated at 0 gives 1. This u over 2 can be taken outside. And then we have the ratio, the first derivative of the characteristic function divided by alpha. Now, what is the first derivative if we take the limit as alpha tends to 0? The first derivative of the characteristic function evaluated at 0, as we have seen, it is I times the first moment. If our random variable is 0 mean, this means that this is also equal to 0. And the denominator is 0 as alpha tends to 0. We are again in a 0 over 0 situation, and we need to apply L'Hopital's rule. And we can do this because the second moment is finite for random variable x1, and hence the characteristic function is twice differentiable. So there is no problem in taking the derivative again. In this case, the denominator, the derivative is 1. The numerator, we will get the second derivative, and by the chain rule, because we are differentiating with respect to alpha, we will get an extra u here. So we have u squared over 2. The second derivative of the characteristic function of random variable z evaluated at 0 is I squared, which is minus 1, times the second moment of the random variable. So in our case here, this, when we take the limit as alpha tends to 0, is minus the second moment of the random variable x1, which is its variance, which is sigma squared. We have a limit. The characteristic function of the sum divided by the square root of n, as n tends to infinity, will converge to e to the power minus half u squared sigma squared. And this is a function that is continuous at u equals 0. By Levi's continuity theorem, we do have convergence in distribution. And basically this quantity, its CDF, converges as n tends to infinity to the CDF of a random variable with this characteristic function. And this random variable is nothing but the Gaussian random variable with a mean of 0 and a variance of sigma squared. Now to the Lyapunov central limit theorem. Here, our random variables are independent, but not identically distributed. They are also zero mean, they have a finite variance, but we want the magnitude of xk when we raise it to the power to 2 plus delta, and delta is strictly greater than 0. We want this expectation to be a finite number. Defining Sn squared as the sum of the variances of the random variables from x1 to xn. So Sn squared is sigma 1 squared plus sigma 2 squared all the way to sigma n squared. Then we want the limit as n tends to infinity of the sum k from 1 to n of the absolute moment of xk of order 2 plus delta. We want this summation divided by Sn to the power 2 plus delta. So this will be the sum of the variances to the power 2 plus delta over 2. We want this limit to be 0. When we do the proof, we will know exactly why this condition is needed. Now, if these things are satisfied, what will happen? We will have convergence in distribution. What is the quantity that will converge in distribution? It is the sum of the x's, summation x1 plus x2 plus x3 to xn. And now we divide by Sn. So we divide here by the square root of sigma 1 squared plus sigma 2 squared to sigma n squared. This summation divided by Sn converges in distribution to a standard Gaussian. Technically, this means that the CDF of this quantity here, as n tends to infinity, will converge to the CDF of a standard Gaussian random variable. Let's study the tools needed to prove this convergence statement. We have the Lyapunov inequality, which tells us that if we have a random variable x, p is greater than or equal to q, and q is positive, then this absolute moment of order q, and then we have the absolute moment of order b. If we raise this guy to the power 1 over q, and we raise this guy to the power 1 over p, then with q less than or equal to b, this expectation is less than or equal to this expectation. Let's apply Lyapunov inequality with q equal to and p is equal to 2 plus delta. In this case, Lyapunov inequality tells us that the expectation of magnitude xk to the power 2, that's the second moment, to the power 1/2, this is less than or equal to the expectation of the magnitude of xk to the power 2 plus delta, and then this expectation is raised to the power 1 over 2 plus delta. Squaring both sides, we get that the expectation of the magnitude of xk squared, that's just the expectation of xk squared, the second moment, is less than or equal to this absolute moment of xk of order 2 plus delta, and then the power here is 2 divided by 2 plus delta. This is this inequality here. Note that Sn to the 2 plus delta, if we raise it to the power 2 over 2 plus delta, we get our original Sn squared here. Now this is a non-negative quantity, and it is less than or equal to the sum if we sum those absolute moments. This is here for xk. Now this is a sum with j from 1 to n, and k is 1 or 2 or 3 all the way to n. So this is just one term in the summation, so the expectation is upper bounded by the summation of those expectations. This is true for every k in this set from 1 to n. Now this is an upper bound that does not depend on k. So we can take the supremum of both sides, and so the supremum of sigma k squared over k from 1 to n divided by Sn squared is less than or equal to this quantity here. Now, if you look at this quantity, it is this mysterious quantity that appears in the statement of the Lyapunov central limit theorem. We need that this quantity approaches 0 as n tends to infinity. We have the exact same quantity here, and it will go to 0 as n goes to infinity. Note that this is a non-negative quantity, so it is lower bounded by 0, and it is upper bounded by quantity that tends to 0 as n tends to infinity. So this means that the limit of this quantity as n tends to infinity is also equal to 0. So that's an application of the sandwich theorem. Note that the characteristic function of xk divided by Sn of u, this is the characteristic function of xk of u over Sn. If we take this characteristic function minus 1 and call it z of k comma n, where k is 1 or 2 all the way to n, then from page 2 we have this inequality which is valid for zero mean random variables. And in our case here, xk is zero mean, and it has a variance sigma k squared. So this is the inequality that we had earlier. And now in our case, this magnitude will be upper bounded by 1/2. And then the argument of the characteristic function is u over Sn. We need to square it, so we'll have u squared over Sn squared. And then we need to multiply by the variance of xk, which is sigma k squared. From here, we know that the supremum of sigma k squared over Sn squared converges to 0 as n tends to infinity. So also this will go to 0 as n tends to infinity. The magnitude of z of k comma n tends to 0 as n tends to infinity. It becomes arbitrarily small as we increase n. The proof idea is that we will take the log characteristic function of the sum of the x's divided by Sn. Recall that Sn is the square root of the sum of variances. We will take the log characteristic function, and it is called psi of u, and it depends on n minus the log characteristic function of a standard Gaussian random variable. So the characteristic function of a standard Gaussian random variable is e to the minus 1/2 u squared. So this one will be minus half u squared. We will take the magnitude of the difference, and the idea is to show that this magnitude tends to 0 as n tends to infinity. It is difficult to deal directly with this magnitude. So the idea is the sandwich theorem. We will upper bound this magnitude, and we show that the upper bound tends to 0 as n tends to infinity. So here is the log CF of the sum divided by Sn, here written as z of k comma n. So this is the characteristic function of xk of u over Sn minus 1. And what we do is we subtract and add z of k comma n. And also we take the log CF of a standard Gaussian and join it in the summation, k from 1 to n. And the idea is that if we apply this sum to this quantity here, in the numerator, we have the sum of the variances. And this is exactly Sn squared in the denominator. And so applying the sum to this term, we get the u squared over 2 term that we have here. So now every term is under the sum. We split into two magnitudes. So we take these two guys together, and we take these two guys together. And by applying the triangle inequality, then this magnitude is less than or equal to this sum involving these two terms, plus the magnitude of the sum involving the other two terms. We upper bound each of these two magnitudes separately. Let's focus first on this. By the triangle inequality, the magnitude of the sum is less than or equal to the sum of magnitudes. If we rewrite z of k comma n as the characteristic function minus 1, we get something that looks like the magnitude appearing on page 2. We have an upper bound on this magnitude. Our random variables are 0 mean, and the variance of xk is sigma k squared. So what is the magnitude of this difference? According to the inequality on page 2, we can upper bound by 2 to the power 1 minus delta, where delta is greater than 0, times beta of delta plus 1 comma 2. And then we have this parameter of the characteristic function to the power 2 plus delta. In our case, we will take the magnitude of u to the power 2 plus delta, and in the denominator, we have Sn to the power 2 plus delta, as we can see here. Then we have the absolute moment of order 2 plus delta, and applying the sum, we will have the sum of those expectations divided by Sn to the power 2 plus delta. This is the quantity that appears in the statement of the Lyapunov central limit theorem. And we see now where this quantity comes from. It is this quantity here. And we need it to go to 0 as n goes to infinity. And so this will be a condition that is needed for the Lyapunov central limit theorem to work. We will require that the sum of those absolute moments of order 2 plus delta divided by the sum of the variances to the power 2 plus delta over 2, we want this to go to 0 as n tends to infinity. In many cases, we just use delta equal to 1. We also need to upper bound this magnitude here and show that the upper bound approaches 0 as n tends to infinity. So we use the triangle inequality. The magnitude of the sum is less than or equal to the sum of magnitudes. And then we have an inequality that looks like this. We have the magnitude of the difference log something plus 1 minus the same thing. Magnitude log beta plus 1 minus beta. Do we have an upper bound on this magnitude? And the answer is yes. Consider beta, that is a complex number, with a magnitude that is less than or equal to 1 over 2. Write down the Taylor series expansion of this log beta plus 1 minus beta. And this Taylor series expansion is valid when the magnitude of beta is less than 1. Well, we are taking the magnitude to be less than 1 over 2, and so it is definitely less than 1. The Taylor series expansion is given by this summation here. The expansion of the logarithm contains a linear term beta that will go with this minus beta. And so we have our sum starting from j equal 2. By the triangle inequality, the magnitude of the sum is less than or equal to the sum of magnitudes. J is greater than or equal to 2. So this means that 1 over j is less than or equal to 1 over 2. we can upper bound 1 over j by 1 over 2. Now this becomes a constant that can be taken outside the summation. We end up with a convergent geometric series. And so this is 1/2, and then the first term is magnitude of beta squared, and then we divide by 1 minus the ratio of the geometric series, which is the magnitude of beta. Note that 2 times the magnitude of beta is less than or equal to 1. Multiplying both sides by -1, then -2 the magnitude of beta is greater than or equal to -1. If we add 2 to both sides, we have 2 minus 2 the magnitude of beta is greater than or equal to 2 minus 1, which is 1. Take the reciprocal of both sides, and this will be that 1 over 2 times 1 minus the magnitude of beta, and this is what we see here, is less than or equal to 1. So this summation is less than or equal to the magnitude of beta squared. But for this to be true, we need the magnitude of beta to be less than or equal to 1 over 2. Can we apply this inequality to our case here? And the answer is yes. Because on the previous page, we have seen that the magnitude of z of k comma n converges to 0 as n tends to infinity. This means that this quantity in magnitude tends to 0 as n tends to infinity. It becomes arbitrarily small. So for n that is large enough, the magnitude here will be indeed less than 1/2. So this inequality is applicable to our case, and we can now replace this magnitude by the magnitude of z of k comma n squared. From the previous page, the magnitude of z of k comma n, which is the magnitude of phi xk of u over Sn minus 1, this magnitude is upper bounded by u squared sigma k squared over 2 times Sn squared. Rather than writing this as a square, I wrote it as the product of 2 identical terms, and then one term is upper bounded by the supremum, the maximum of those quantities. Now this becomes independent of the index of summation, so I can take it outside the sum. We end up with the supremum, and then we have the summation. What about the summation? The summation itself is 1, because Sn squared is the sum of the variances. And so we end up with u to the power 4 divided by 4, and then we have the supremum of sigma j squared divided by Sn squared. This supremum is for j from 1 to n, and the summation is unity. What about the supremum? We have seen that this supremum tends to 0 as n tends to infinity. Let's summarize what we have done. We computed the log characteristic function of the sum of the x's divided by Sn. We exploited the fact that the x's are independent. They are not identically distributed, but they are independent. This allowed us to write down the characteristic function as a product, and log of a product is sum of logarithms. So we have this summation here. We took this guy minus the log characteristic function of a standard Gaussian. And then our method was to take the magnitude of this difference, upper bound it, and show that the upper bound tends to 0 as n tends to infinity. We subtracted zk comma n and added it, and we joined this to the summation. We split this magnitude into 2 magnitudes by employing the triangle inequality. Then for each one of those guys, after applying the triangle inequality again, we did further upper bounding, and we obtained quantities in the upper bound that go to 0 as n tends to infinity. Note that we needed that the limit as n tends to infinity of summation k from 1 to n, and then this expectation of the magnitude of xk to the power 2 plus delta, and delta is positive, this divided by Sn to the power 2 plus delta, we needed this limit to be equal to 0. And this limit being equal to 0 is actually used in showing that the supremum of sigma j squared over j divided by Sn squared also tend to 0 as n tends to infinity. This difference here goes to 0 as n tends to infinity. So the characteristic function converges to e to the minus u squared over 2, which is a function that is continuous at the origin at u equals 0. And this is the characteristic function of standard Gaussian. So what is our result? If we have a sequence of random variables, those are 0 mean and independent. And we have basically that this summation here, every one of those absolute moments is finite number. If we take this summation, divide it by the sum of the variances to the power 2 plus delta over 2, take the limit as n tends to infinity, this is 0. If this is satisfied, then indeed the sum k from 1 to n of xk, if we scale this sum by dividing by the square root of the sum of variances, then this will converge in distribution to standard normal. To be precise, the CDF of this quantity here tends to the CDF of a standard Gaussian random variable as n tends to infinity.